Hello students, today I am to discuss about the noise figure. This is the another parameter of the device, receiving device. Then suppose this is the amplifier, the receiving device, okay. The input signal is SI, input noise is NI, input output signal is S0, output noise is N0. Okay, so noise figure is basically defined by signal to noise ratio is in the input side to the signal to noise ratio at the output side. Okay. By this noise figure, we can get the idea what amount of extra noise is contributed by the amplifier. Okay, the amplifier introduces what amount of noise each can we can get the idea from the noise figure. Okay, in practical cases, we have seen that the noise figure value is greater than equal to 1. Okay, but if this value is low, that means lower the value of f means the amplifier is the good performance. Okay, suppose my amplifier reduces amplifier given less noise, that means the denominator ratio gives the higher value, that means the noise figure gets value less. Okay, now the again there is another parameter is the noise temperature. Okay, the temperature generated inside the device or receiving device due to the noise is called the noise temperature. Okay, here I am giving an amplifier. This is the input side, this is the output side. The temperature generated inside the amplifier is equivalent. This is the noise temperature, and outside of the amplifier the temperature is T0. Okay, so the noise power, if I noise power by the amplifier by the noise figure formula, the formula is f minus 1 k T0 into B, and we know that the noise power inside the amplifier is k into t equal into B. Okay, the noise temperature into B. So if I equal these two terms, then the noise temperature, we can write this temperature formula f minus 1 into Tj. This is very important formula. Okay, students, this noise chapter has a very small formula. Okay, so by the using this formula you can do so many problems. Okay, in a competitive exam or the gate exam, so many problem comes from this noise chapter. Okay, so be careful about the this formula. All formula I am giving, these are very important. Okay, suppose you done a problem here. A amplifier has a bandwidth. A amplifier has a bandwidth 4 megahertz, which has the input resistance 4 kilo ohm. Okay, so calculate the RMS noise voltage at the input of the amplifier when the room temperature is 20 degrees centigrade. Okay, so RMS noise voltage, that means Vn equal to root over 4 kT B into R. So we know all the value. K is a Boltzmann's constant, T the room temperature. Okay, room temperature in Kelvin, B is the bandwidth, R is the resistance. So we get the noise voltage is equal to 25.64 microvolt. So we can get very less voltage is generated due to the noise. Okay, another formula is there, another problem is there. Okay, calculate the thermal noise power from the any resistor, at room temperature 290 k Kelvin for bandwidth 2 megahertz. Okay, in this case we have the T temperature, the bandwidth. Okay, so my noise power formula, we know that K into T into B. So K value is the Boltzmann's constant, the temperature in Kelvin, and the bandwidth and is given here. So we get the noise power is 8 into 10 to the power minus 15, very less power generated due to the noise. Okay, this is what. Okay, so this formula, from the noise chapter, the problem is very important. Okay, which comes in the competitive exam or the gate exam. So remember the formula, all formula in the noise chapter.